ahead and get started for our afternoon session. Our first speaker we have is Kristine Uhlman with Texas AgriLife Extension Service. She's going to be talking to us about our Texas Well Owner Network.
Today, John Smith, and Brenda Clayton. So the goals of the program is to provide changes in knowledge of the individuals who have their own domestic wells. And as you know, a domestic well is exempt from regulation. The only requirement is that you have to pump, for example, less than 25 gallons per minute. That means to install a well that pumps less than 25 gallons per minute and provide water supply for domestic use. That water cannot be sold, and that water can also be used for other agricultural purposes, but there's some limits on the quantity of water to be used. But in any event, the goal is to provide education and knowledge to assist those who own their own private water wells and water well systems to implement best management practices to protect and improve the aquifer integrity, but also, very importantly, because these are exempt wells, the individuals are responsible for the monitoring of their own water quality. Nobody's looking after them or over them to make sure the water they are drinking is safe. So our approach is that we have gathered information from several other programs across the United States, including already successful programs in Pennsylvania, Virginia, Rhode Island, Arizona, and also to update some of the Texas publications. Are any of you familiar with the round of Texas publications that were generated by AgriLife Extension? Well, they'll be updated and they'll be helpful. What they do is that they recommend best management practices to improve water quality. What's interesting about the list of some of the other extension programs across the United States that have implemented similar programs, the one I like the best is Montana, because they call their program the Well Educated. Wouldn't that be cool? So let's look at how our training program goes. We are going to be reaching a broad audience and doing 6-hour workshops. As part of those workshops, we will be doing water quality screening of well water samples that are brought into the workshop. This complements a program that has already been developed and maintained by John Smith here, handing out some publications. And so John Smith has been going across the state, as you may well know, doing well screening programs. The educational programs will have PowerPoints, screenings. We also have a nifty sand tank model that looks like an ant farm, where we can show various aspects of how the aquifer responds. In Texas, talking about aquifers, we're also going to be introducing some of the information already available on major and minor aquifers in Texas. A major aquifer just means that it's a large aquifer that provides water to a large number of people. And a minor aquifer is a smaller aquifer that provides water to a lesser number of people. The location you can see on this map circled is about where we are today. Groundwater is managed by a total of about 96 groundwater conservation districts across the state. And this map shows some of the conservation districts in our area. And that number will increase over time in terms of the number of conservation districts. A key component of our outreach program is to assist the public to understand what is an aquifer, what makes an aquifer. So we start with the basics. Tectonics, plate tectonics. How many of you are familiar with the idea of these continental plates rotating around the planet, bumping into each other, yes. Now, we'll explain how those make aquifers. We look at this map of Texas from space, and here we can see rift valleys along the Mississippi and along the Rio Grande. This is the result of plate tectonics. What plate tectonics do, as you know, interior to the Earth, there's these big cells of magma that are rolling and trying to get out as a volcano and moving the plates around. What these circulations in the interior of the Earth are doing is that they're also sinking, pulling down the Gulf of Mexico, punching up the western states, and pulling the continent apart like this. Millions of years ago, there started to be a rift valley that started in Hartford, Connecticut, going all the way down to the North and South Carolinas. What was happening is that the continental plate, which consists of really thick, buoyant granite that goes from Mexico to Canada, it was being pulled apart. As it's being pulled apart, the crust thins and breaks. And that's what started to happen along the east coast of the United States. Then it moved 50 miles to the east and formed the Atlantic Ocean. That rift valley is continuing to pull apart at a rate of about 1 inch a year. So over a lifetime, if you're traveling from New York to London, the distance will increase by about 6 feet. And that's how we explain the increase in airfares. So another rift valley began to form along the Mississippi Valley. So as we pull the continent apart, it starts to sink and subside. And of course, when it starts to sink and subside, that's where the rivers form. That's where the water starts to drain. So we have the crust thinning, 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 sinking, and then everything draining down to the Gulf of Mexico where everything's sinking. We have another rift valley that forms along the Rio Grande. And that one has actually fractured a bit. Maybe some of the interesting topography that you see along the Rio Grande. And so they're trying to measure the rate at which that is pulling apart. Up in Albuquerque, they're trying to measure it. It's a little bit less than 1 inch a year. They don't really have an exact number. Here we have the Colorado Plateau. That's where things are being punched up. So we've got things being punched up. We've got things being pulled down. And then we have my favorite, the San Andreas Fault. And here you can see some really exciting action with the continental plate. It's pulling apart, slipping and sliding along the San Andreas, and smashing into Portland and Seattle. So at this point, I have a question for you. When you look at this area, let's say right around Missouri, Arkansas, or this area up here, Seattle and Portland, which is most tectonically active? How many vote for Arkansas? How many vote for Seattle, Portland? Arkansas is the answer. Arkansas is the answer. There are multiple, up to like 12 earthquakes a day in that area. They're all less than about 2.2, maybe 3.8, a couple of 4.2. But there's earthquakes all the time, right along the New Madrid fault. 1812, there was a huge earthquake. They think it was about a 9.2, but it was such a strong earthquake that it actually rang church bells in Toronto. And it changed the course of the Mississippi Valley. So these earthquakes indicate to us that this is still stretching, dropping, and then to some extent controlling the surface water drainage of this part of the United States. Now up here in Seattle and Portland, when there's an earthquake up there, it's going to be a big one. It's going to be like what happened in Japan, because things are slamming together as opposed to pulling apart. So what's important to know about this in terms of building aquifers is that we've got drainage and transport of sediments here, erosion, transport of sediments here, and there's uplift in the center of the state, in the very center of the state where we have the granite in Llano County. Now it won't obey me.
Click that one.
Click which one?
The mouse.
The mouse.
Yeah, the mouse and the arrow.
Ah. So when we look at how this sediment is being eroded from the highlands and transported to the lowlands, we get the typical Texas aquifer. So generally it's true that anything east of Route 35 has an aquifer that looks like this. We have dipping sediments going to the south and the east, and we have a series of aquifers and aquatards. Aquatard just means that the water is retarded. It's slowed down. So that way we get recharge areas here, and then recharge gets into the aquifer, and that's how we have the layered aquifers that we have in the eastern part of the state. So when you look at this type of hydrogeologic setting, we also have artesian wells. And artesian just means that the head in the aquifer is over here in the recharge area, and that head is expressed all the way across through the system, meaning that when you punch a hole in the aquifer here, the water wants to find its level and come on up. So in artesian well, the water goes up above the aquitard, the layer that is confining that aquifer. It may or may not go all the way up to land surface. Then we talk about what makes an aquifer in terms of the geologic material. So the example I showed you is the eastern Texas aquifers that are being built by erosion, sedimentary transport because of the pulling down of the Gulf of Mexico and the transport of these sediments, which are typically unconsolidated aquifer material. Unconsolidated means that if you were to dig at it with a spoon, it would come apart. But over time, as the sedimentary material is buried and squeezed, it lithifies, it becomes a rock, which would be a consolidated aquifer material. The water is held in the spaces in between the sand grains and gravel, for example, what you see here. So you either have a well-sorted, unconsolidated aquifer, which would be like old beach sand or sand dune, where all the material is about the same size, and you can get a lot of water stored in those spaces, and you can get a lot of water out of those wells. Or you have a more jumbled up mess of poorly sorted sand and gravel. And that's what you tend to get when the mechanism of deposition is a combination of wind, rain, and gravity. For example, what we see over in West Texas. But as the material becomes rock, the water is held in the secondary porosity. In granite, for example, there's more fractures and cracks the closer you get to land surface. So if you put in a well in granite, the deeper you go, the less water you're going to get because the water's in the fractures and cracks. If you're in the Edwards Aquifer, for example, you have a limestone aquifer where water flows through those fractures and cracks, and as it flows through that material, it dissolves the rock and makes caverns. And so when we talk to the public about what type of aquifer you have, are you in consolidated or unconsolidated, we give examples like this, and we talk about the vulnerabilities of different types of aquifers to contaminant transport or to loss of capacity during drought. So this is an example of unconsolidated sand, and here it is becoming more consolidated. This, by looking at it, you can tell it's an old sand because you can see the slope of the different bedding planes. And then this is more of a jumbled mess with unsorted sand and gravel. All of this material makes for excellent aquifers when there's water in it. This is another example of what the inside of our aquifers look like here in East Texas. And you can see that there's different layers that were deposited over time. Some are more consolidated than others. Most likely in this setting, we've got some limestone up here. And the material is just layers and layers of unconsolidated material. And if it's deeper in the aquifer, it becomes more consolidated. And then, of course, this is an example from the Edwards Aquifer. We get totally consolidated rock, and the water is held in the fractures and cracks. So another thing that's important to talk about when you're talking about aquifers is how rapidly does water flow through that geologic material. And here's another example, again with unconsolidated aquifers to the left and consolidated rock aquifers to the right. And you can see there's a great deal of geologic variability in these aquifer materials. So let's look at some sand. Can someone read to me how rapidly water can flow to a well in sand?
3 feet per day to 3,000 feet per day.
3,000 feet per day. Think about that. If you have a well and you have a septic system, and you're pumping water from as far away as 3,000 feet away underneath your septic system, what are you drinking? And so when we talk about aquifers and vulnerability to contamination, we tie in some of the aspects of septic systems and hazardous materials management and waste material management for the homeowner or ranch owner or well owner. Let's look over here at rock. I like rock. That's a very generic term. Let's assume it's granite. So can someone read to me how rapidly water flows through rock? Are we digesting it? 1 foot in 100,000 years to 300 feet per day. So still, if your septic system is 100 feet from your wellhead, you could still be drinking what you're flushing. Another important thing to look at is clay, which is an aqua tar. It slows down the rate of water flow. And when you have a clay layer in between your aquifer and your land surface, your aquifer is confined because water only goes through at 1 foot per 10,000 years or a tenth of a foot per day. So part of our program, we talk about some of the regulations in Texas and the construction details for a domestic well and the appropriate distances for different aspects of your domestic well. We also talk about what are those things at our wellhead. Storage tanks, power supply, the steel casing, sanitary seal of your well. All of this is being covered, and these same photos are in the Texas Well Owner Guide Handbook, which is very similar to the Watershed Steward's Handbook. And all of this information will be published. We're going to be looking at the galley proofs probably next week or the week after, and then the entire publication will be published and available probably by the end of August. Another aspect of our program are well screenings. Here you see John Smith again doing some of the well screenings. Now when we talk about what are the most likely contaminants to show up in a domestic well. No, whoa, I don't like this guy. Okay, the most likely would be bacteria or pathogens. This would be due to ponding of surface water, for example, around your wellhead that allows surface contaminants to seep down into the aquifer. Or it could be to failure of your septic system. Another more common contaminant would be nitrate. Again, that could be originating from your septic system. It could be originating from land use practices, non-point source application of fertilizers, or it could also be naturally occurring. Another aspect, as we all know, of groundwater in Texas is that there tends to be a lot of salty water. So that would be also measured during these classes. In Texas, we have a number of naturally occurring constituents that can be a health concern. Number one would be arsenic, naturally occurring arsenic. And number two would be radionuclides, most importantly generating radon gas that would be dissolved in your drinking water. I spoke with a woman a couple of months ago. She was in chemotherapy because she had lung cancer. And the doctor said, I don't understand why your blood levels are so high with arsenic. Let's do a test. And what was really quite sad for this woman, she never smoked a cigarette in her life. When they did a complete water analysis of her well water, her water had very high concentrations of dissolved radon gas as well as arsenic. So the arsenic generated the arsenic problems in her blood. Arsenic tends to duplicate some of the symptoms you have with diabetes, but the greater concern was radon gas. Now, in a public system, radon gas has more of an opportunity to dissolve out of the water, to vaporize into the atmosphere. But in a private well system, it doesn't necessarily have that opportunity. So every time you flush a toilet or step into the shower, you are exposed to radon gas, and with a half-life of 2.5 days, it gets into your lungs and then changes to a metallic radioactive material. So that woman's well water was explaining her health concerns. Okay, now it doesn't work again. Help me. Okay. Okay, so part of the, so clicking it, it's not obedient. Part of our training is also to provide information about point-of-use treatment systems. Water treatment systems that you can put into place to take care of some of these water quality issues. And here's a graphic from our book that talks about, for example, if you have arsenic, reverse osmosis would be the best filtration. If you're wanting to filter out Giardia or bacteria, there's other treatment systems. Let's see if this works. Yes. So when you talk about wells, you also need to talk about how the water moves through the aquifer and how that could capture and move contaminants in the subsurface. So we talk about drawdown, or the cone of depression. It's called the cone of depression because it's drawing down or depressing the water table. Every time you turn on a pump, the water table immediately around the well drops down, forms a drawdown cone. And as you continue to pump, that drawdown cone expands, 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 reaching further out to get water to come into that well. So with the cone of depression, or the drawdown cone, an important thing to realize is that when you have closely spaced wells, those drawdown cones overlap, and it exacerbates the rate at which the water table drops. Now, I've talked about drawdown cones a lot with the public, and after one discussion, a woman came up to me and was talking about, what do you mean about cone of depression? Is that how you make coffee? Is that cone of coffee? So no, cone of depression, you draw down the water table, it's depressed. And here in the West, what the problem we have is that the interaction between surface water and groundwater is that as the water tables drop, as the water tables are drawn down, the rivers go dry. This has already happened in Arizona, where there's so much groundwater pumping, the rivers go dry. And here in Texas, with ongoing drought and ongoing pumping, that will continue to be an issue. And here's another example of overlapping cones of depression, drawdown cones, exacerbating the rate at which the water table drops. So when we talk to the public, we like to talk about what's in your cone. When you go out to your wellhead and you look around, what's in your cone? This example is from a ranchette where individuals were going to put in a water well, and they wanted to put it away a distance from their septic system. So they went over the hill and they put it right next to where they keep their animals in their barnyard, which was a mistake. But then they felt quite confident as they drilled down because they hit the clay aquifer. So they thought, our aquifer will be protected. It will be confined from any surface activities, will be safe. But what's amazing about geology is that it's unpredictable. Here we have the aquifer, and it pinches out. So every time these people turned on their pump, groundwater direction went right there, picking up some of the animal waste, the pathogens, the salts, the nitrates, and also from their septic system. But another thing that's important about land use activities and water, groundwater, is that, for example, if you're storing diesel or fuel, if there's an inadvertent release to the subsurface, that's going to float on the water table, and small concentrations of toluene, benzene, xylene, All cancer concerns will dissolve into the water. And also solvents. Do any of you do engine repair and use those nifty little degreasers? That's chlorinated hydrocarbon. That's the same stuff they use in dry cleaners. Chlorinated hydrocarbons are denser, heavier than water, and so they sink rapidly, continuing down. When they hit clay, they physically change the structure of the clay. They make the clay porous. So they zip on through, and they continue to contribute part per million or part per billion concentrations of chlorinated hydrocarbons that are cancer-forming. Have any of you seen that John Travolta movie, A Civil Action? Okay. What caused the leukemia in those children was this stuff, chlorinated hydrocarbons. All you need is a little bit. So, we talked to the public about trying to develop their own wellhead protection zone, managing their land use activities in the area around their wellhead. A lot of small communities are also doing this. What they do is that they identify the maximum extent of their drawdown cone or their cone of depression. And within that area, they identify that as a wellhead protection area. They zone it so that there cannot be any gasoline stations, chemical plants, dry cleaner facilities, because they don't want an inadvertent release of contaminants to get into their well. And we advocate to the private well owner that they take the same approach. You do not store gasoline, you do not store herbicides and pesticides or any chemicals of concern within the area around your wellhead. Another aspect of our educational program to the private well owner is that we talk about drought and how drought impacts not only water quantity, but water quality. And so here's when we were at our maximum drought last September. It was a bullseye on Texas. The result continues even today. This is as of last May. Here we are. You can see that many public water providers continue to be under drought voluntary or mandatory watch, meaning water use restrictions are in place or they're having issues with line pressure in their delivery systems. So drought has an impact longer than just the fact that we didn't get rain last summer. The other impact you can see on the water table elevations. We talk about in the program hydrographs. And a hydrograph is basically a way to present data that shows change in groundwater elevation over time. So on this screen we have elevation of the water table, and here it goes from April till October 2011. This is last year. And measurements are taken and reported by the Texas Water Development Board. You can get this on the internet. It's kind of fun. You get on the Texas Water Development Board and you hover over one of these wells. These are all of the wells in Texas that are being monitored by the Texas Water Development Board, and the data are available. Just get on their websites and you can print out the hydrographs. So what do we see on these hydrographs? I like this one. It's very simple. Well, here we go, and we get into the drought. There's no rain, we're not getting recharge, and the water tables are dropping. And then in early September, it rains, and the water table goes up. The same thing here. Water table starts to go up. Water table starts to go up. That is an aquifer that is most likely, the well is within the recharge zone, because the well, the hydrograph, the depth to water is very responsive to precipitation. When it rains, the water goes up. When there's drought, the water goes down. Kind of vulnerable, don't you think? There's a drought, you're going to have troubles with water supply. Oh, this thing is not obedient. So we look at an alternate situation up on the Ogallala, up on the Panhandle. This is the Panhandle of Texas. And this is the well up here, right smack dab in the Ogallala. And what's happening? Let's look from January 2011 to October 2011. And you can see the cycles of pumping on and off, on and off, on and off. And then everybody's pumping because there's no rain. Don't look at from 1994 to 2012. We see the same cycle, seasonal cycle, a lot of pumping when they're irrigating, but the overall trend is down. A significant drop in water table elevations, almost exceeding 25 feet in the Ogallala. What's happening there? It's vulnerable to drought because more people are pumping during the drought. In fact, last year, the average drop in water table elevation was 2.5 feet, and it's not recovering. So how do we understand that? How do we communicate that? How do we give the public information to understand what this means? And the way we like to talk about the need for water conservation and water management is to talk about isotopes. Now, talking about isotopes to the public sounds like a scary thing, but I've been doing it for about 6 years and no one has yet told me to stop because it's quite simple and straightforward. We look at the water molecule. The water molecule consists of H2O, hydrogen, and oxygen. There's several isotopes that we can look at to understand the characteristics of this water. We can look at other things that are dissolved in the water. But today we're just going to look at the hydrogen. The water molecule with hydrogen attached to it. Hydrogen has 3 different isotopes, and you can think of an isotope as 3 varieties of the same thing. One is thin and one is fat, for example. So with hydrogen, the isotope we're looking at is tritium. And tritium is hydrogen with 2 neutrons, as opposed to just a regular old hydrogen atom. The half-life of tritium is 12.3 years. If I have a bucket of tritium, what do I have in 12.3 years? Half a bucket. Okay, if I have half a bucket of tritium, what do I have in another 12.3 years? Quarter of a bucket. So we understand the rate of radioactive decay, but where does this tritium come from? We made it ourselves. Back in the 50s and the early 60s, we were testing nuclear weapons in the atmosphere. We were bombarding our biosphere with radioactivity. And what that radioactivity did is it made water molecules into tritium. Now, today we continue to generate some tritium around some nuclear power plants. But the big guys, that's what's kind of interesting to hydrogeologists. Here we look at some data from Ottawa, Canada. Here's from Miami. Those little crosses are measurements taken of the radioactivity of rainfall. Those black dots are nuclear weapons explosions. There was the 1964 Nuclear Test Ban Treaty. Everybody tried to get their weapon tested before then, but then too there's a few bad guys after that, bombarding our biosphere with radioactivity. To the joy of hydrogeologists, because we can use that information to track when was the last time that raindrop was exposed to the atmosphere. So we can do this all over the planet. Here's from Miami. You can see, looking at the scale is logarithmic. You have to have 30,000 tritium units in water for it to even give you a little bit of indigestion. So this is not a health and safety issue. This is an issue where our inadvertent scientific experiments in the past give us a good tool for understanding groundwater. So generally, knowing that the half-life is 12.3 years, knowing that we began to inject the atmosphere with tritium in the 1950s, we know if we take a sample of groundwater and there's no tritium, that water fell as rain before 1950. If there's some tritium, we can calculate when it fell as rain. If there's 2 or 3 tritium units, it probably fell as rain yesterday because that is how much is naturally occurring. So how can we use this information? We can look at the hydrologic cycle. We can visualize rainfall falling out of the sky, going over the land surface, seeping into the soil and water, and taking some time as it travels through the subsurface. We know that starting in the 50s and 60s, there was a great deal of change in our land use activities. A lot of contaminants were released into the environment. A lot of inadvertent activity that resulted in dangerous chemicals being released at land surface, as well as some non-point source activities, agricultural chemicals being released at land surface. So you can make the general assumption that any rain that fell during the 50s and 60s would most likely come in contact with some contaminants. So it would be more likely to be vulnerable to contamination. So the younger water is more vulnerable. The older water is less vulnerable, although there are some contaminants that ignore that. Remember the screen showing the chlorinated hydrocarbons. So how can we use this? The city of Los Angeles went around and sampled every one of their drinking water wells to determine the probability or the vulnerability of that water supply to land use activity contamination. And so here they have their data from the tritium information. If it's red, it was between 4 and 9 years old at the time of sampling. Green, 25 to 30 years old. Purple, which you can't see because of this interesting little thingy, means there is no tritium. So what they did is that they mapped their aquifer. They showed where there was younger water, more recently recharged, more likely to have come in contact with surface contaminants, and then the older water, which is less likely to have come in contact with surface contaminants because it fell as rain before 1950. Based on this information, they revised their monitoring of their drinking water supply, increasing the frequency in those wells that were more vulnerable, and decreasing and focusing only on certain contaminants on the older wells. They saved money. But also, using this technique, we can understand how vulnerable drinking water wells are to surface contaminants, and that work has been done in Texas. And we characterize it along the lines of, do we have a vulnerable system that responds to rainfall, young water? Is that a checking account? For example, when you're living off a checking account, you know you're getting a certain amount of money or water into the system on a regular basis, and you behave accordingly. But if you're living on a savings account, you have a certain volume of water or a certain amount of money, and you have to live within your means. So working with tritium isotopes as well as oxygen, helium, carbon-14, there's been a lot of work done, mostly by the U.S. Geological Survey, that identifies that you have exceeded your profile storage space, that identifies the age of groundwater resources. And what do we have near El Paso? Groundwater that's 12,000 to 25,000 years old. Up here in the Ogallala, right now they're pumping water that's 2,000 to 6,000 years old. That means that water's not being recharged. It's not recent water. What they have found in the Carrizo-Wilcox over here, in the recharge area around here in the Brazos Valley, the water is very recent. There's tritium in it. But you move 35 miles to the east, the water is 25,000 years old. So, in communicating the need to conserve water, to manage your water resources, and also to assess the vulnerability of your aquifer to contamination, you characterize that resource as a savings account or a checking account. Can't be dramatic when whatever. So, in the Ogallala, it's a savings account. Current estimates are that the water will be gone in 40 years. 40 years. That's a generation. The farmers that are managing their resources on the land today will not be able to transfer that richness to the next generation, because there will be not enough water to farm on the Ogallala. Here on eastern Texas, where we have our aquifers that are receiving recharge in the recharge area, that's young water, and water is moving downslope. We have a checking account here, we have a savings account here as we move further down dip. So we have greater vulnerability to water quality issues as well as water quantity issues. These guys over here, they'll be able to pump for a while until it's gone, and then there won't be any more. So there you have it. Thank you very much. And if you're interested in the T1 program, I suggest you speak with Diane Bellstorff. Diane, wave your arms, as she is the program lead for the T1 program. Thank you very much. Any good questions?
Yeah, we have time for a question or two while we're switching for the next presenter. Any questions?
Ah, they're all well educated. Oh, yes.
I've got I guess the question is about like water filtration systems, like either a big one or say you have like a Brita water filter or something like that. How effective are those on reducing contaminants?
The question is how effective would be, for example, a Brita water filter for reducing contaminants. And it's going to be contaminants. For example, a Brita filter will not take care of PFAS or a lot of salt. It might take out a little bit of lead, and it's really good at taking out fluorinated hydrocarbons as long as it's very, very small concentrated, and also chlorine. So part of our program is to talk about the different treatment systems and the importance of first test the water, see what's in the water, and then put the appropriate treatment system to address the problem. Any other questions?
So this should
Yes,
change the slide. Right. She wanted to use hers because it had it better.
Because of the development of the well, or is it because you have one of those sandy structures?
Okay, the question was about a well pumping sand. When you install a well, especially if you're spending a lot of money, like a municipal or industrial entity, as you're drilling the well, you look at the sand grain particle distribution in the geology, and then you size the screen or the slots in the screen to reduce the potential for that sand to come into the well. That typically does not happen with domestic wells. All wells, no matter what the purpose is for, after they're installed, what the driller does is something called development. That means you pump the well harder than it will ever be pumped in its life, and you try to suck out as much sand as you can, and you pull that out, you develop the well, and then you put in the pump, and you use the well at the rate as appropriate. Now, if you have a well that's pumping sand from day one, it means the well was not appropriately designed or developed. If you have a well that's pumping sand a year, 10 years, 20 years after it's installed, what that means is that the water table has dropped, it's changing the hydraulics around the well stream, it's eroding the well stream, you're pulling in sand, you're brightening up your pump, and you're in big trouble. Okay, is the next speaker ready?
Yes, ma'am.
There.
Okay, our next presentation is Jessica Snyder with the Texas Stream team, and she's going to be doing a presentation about their data viewer and taking us on the internet to show us how it works.
Can everyone hear me? Good afternoon. My name is Jessica Snyder. I'm with the Texas Stream team. And for the next about 30 minutes, I'm going to be introducing you to our online data viewer. Before I begin my presentation, I'd like to introduce one of our new employees, Mr. Travis Tidwell, as our new volunteer coordinator. So, welcome. Please go and talk to him after the presentation. He wants to meet everyone. The Texas Stream team is a network of trained volunteers and their supporting partners who sample water quality across the state of Texas. It was established in 1991 under the name Texas Watch. The name changed several years ago and is now the Texas Stream team. And it is a partnership between Texas State University, River Systems Institute, and our major funders, the Texas Commission for Environmental Quality and the U.S. Environmental Protection Agency. So members of those, thank you very much. It is headquartered at the Texas River Systems Institute at Texas State University in the city of San Marcos. Earlier this year, the Texas Stream Team introduced its online data viewer at aqua.rivers.texasstate.edu, which we'll be joining here in a few minutes online. And this system was developed by LCRA and Texas Stream Team with the goals to help increase the interaction and accessibility between monitors and their data, and to increase ownership and participation of monitors, groups, and partners to the Texas Stream Team program. The data viewer accomplishes these goals by allowing users to view historic and current data from active and inactive sites, to enter and proof data online, and to update group, site, and personal contact information online. Any user going on to the website, which you'll see listed here, can view all historic and currently active sites, can locate sites by basin, that's the TCQ basin, our region, defined by the major city nearby, can view and download data from each site, and can view all sites managed or sampled by a specific group or partner. Some possible uses for the data viewer include for monitors and stakeholders to download and view the information on their local rivers, for educators to use the data in STEM-related projects using local or Texas information, for government agencies to supplement water quality monitoring to their professional sampling, and for cities and counties to use it in water management planning. I'm going to go ahead and exit out of PowerPoint and go right into our data viewer. So as I was mentioning, any user can query by basin, map, or region. If we select our basin, we're going to look at the Brazos and look at one of our sites, click on the site, and you can see current information and historic information. Going back to our original map, red sites are currently active sites, gray sites are inactive sites. You can do stream overlay, and as you continue to move into the map, you see streams coming into focus. You can do either map view or satellite view to view your system. You can also look at county boundaries and wastewater outfall systems. In addition, if you're hoping to view all the sites that say the City of Dallas samples, there are all of those sites that the City of Dallas helps manage and sample. And then by clicking each one, you can again see their data. So the next part of the presentation is actually to join the Texas Stream Team. Once you join the Texas Stream Team and you've been approved, you can continue and enter data, have access to more more information, etc. So I'm going to just enter here first name, last name, title, I'm the data manager, affiliation, Texas Stream Team, my university address, all of this information is then put into our database, allowing a reduction in some of the time that we're spending doing data entry for every time that we have a monitor coming in. If they change an address, they are able to actually go in and update their own information instead of having to contact us. They can also choose their affiliated partner and their group. I'm going to choose to join the Texas Stream team, since that's the group I work with. They can choose to subscribe to an e-newsletter. That is then sent over so it automatically updates into our system and sends them a newsletter. And also if they are a teacher, so that if we have trainings nearby that can allow them to get TH credit, we can notify them. From there, you're asked for your username. Monitors create a username. There's mine. And create a password, confirm the password, and then create an email. Your information is then emailed directly to your email account, and within 3 to 4 days, we approve you for a certain level. I've gone ahead and logged on as a couple of different levels. So the levels that we have for the program are monitor, group leader, partner, and admin. So logging in as a monitor, this would be any monitor who's been trained and is actively sampling a data site. No, I don't think. And they are able to view their training information. I just happened to get trained today. I guess that was this morning. I can look at my contact information, and as I was mentioning, if I end up moving, it's no longer something where I have to contact the Texas Stream team. We have to work it through our system and get it updated. They can update automatically, and that then goes out to all of our database systems. And finally, if I've just monitored my sampling site, I can choose to go in. Here is our data sheet. It is pretty much exactly the same as our physical data sheets, and enter in my sampling data and hit submit. I'm currently not assigned to a site, so nothing comes up. If I were assigned to a site, once I've been assigned, then my name comes up and my site comes up, and I only have access to the sites that I monitor. Once a monitor hits submit, it goes into our system. It is then proofed by a group leader and then goes into the database. So I'm going to sign out and sign back in as a group leader. And group leaders are those that are either head of a sampling group, have been trained on quality assurance and how to proof the data, etc. Group leaders can create or adjust their group. They are not allowed to actually work with the information from any other group. I'm listed with the Texas Stream team, so I can assign myself as the contact, and Travis, you're the new monitoring coordinator for our group. I can also put in any comments, talk about the date created, etc. Anything that you think that a group leader might think would help our team. Group leaders can also update site information. So most of our sites are in Hays County. There we go. See a list of all of the sites that are located within Hays County. They appear on a map, and here's all the information about those sites. It does not include any data. This is just defining where the site is. If a team does need to change where a site is, say that this pointer is actually a little bit wrong and needs to be on that lake right there, pointer can be moved, automatically adjust, and the group leader has now updated the site. They can assign monitors to sites. So I was talking earlier about needing to be assigned to a site. If I go down into Hays County, I can assign my monitor to this site. That means I am able to now enter information about that site. They can, group leaders can also, of course, enter monitoring data. They can also proof monitoring data. Once a monitor submits data, the quality assurance officer will review that data, make sure that there's been no typos. If there are any problems with the data, say they did not calibrate their conductivity meter prior to sampling, it can be flagged so that we know that there is a problem with that data. and then in the database, that flag remains. Along with updating their own contact information, group leaders can also look at all of the volunteers within their group. So if a group leader knows that a volunteer has moved, the volunteer doesn't seem to be updating the information, the group leader can now go in and update that information for the volunteer. The next level up is partner. Partners many times oversee several groups. R may only oversee one group. And I'll be logging in using the partner and the admin. Admin are pretty much only the people that are working with the system at our offices. Partners have almost the same rights, other than partners cannot create sites. Only we can create sites, and this is just to ensure that groups don't go in and create numerous sites that they may not be monitoring. And again, partners and admin can assign partners in groups. So if you have a person who has not signed in, here's some of our volunteers. If we find that David has not actually signed on to his group, we can go ahead and assign him to a group. We can create groups and have access to all the groups that our partnership oversees. We can update sites. Again, if a group wants to create a site, they need to contact our office. They can assign monitors to sites. They can add monitor training information. So if a partner does the actual training, such as several of our partners do, they can update their monitors training information from there. And they can do all of the other things that have already been mentioned. Admin, of course, we have all of those capabilities along with overseeing the system. Unfortunately, we have had a few problems that we're working through right now. Like any new program, it has a few little glitches. We've had server errors where people put in too many decimal places, and the program is a bit picky. So when they go to enter monitoring data, it's still a work in progress, but we are working on getting that fixed, and hopefully we'll have a fix within the next week or two. Going back to the PowerPoint for just a moment. Again, this is our address if you would like to go visit. Make sure you do have the S at the end of HTTP. This is a secure site. If you do not have that S, it will not open. And the data viewer appears to only like Mozilla. Will not work with Internet Explorer, and it's not real happy with Google Chrome so far. Links to other tools. We have our link to our actual data viewer. It's also on our website. We have our online modules. This explains anything that a monitor, group, or partner might need. And our Facebook page that keeps everyone up to date, etc. Are there any questions? Would you like more explanation on something? Anything of the sort? Yes, sir?
When you showed us data sites historically, was this the data from volunteers only, or is it a combination of volunteers and then the data that's in the integrated system TC?
No, this is only volunteers, and currently it's only volunteers within the Texas Stream Team program. Yes, ma'am.
Is this training now been added to their basic training, the first, second, third? When do they get training on how to use the data viewer?
Currently, we only have a PDF to explain the different processes. Eventually, we probably will be creating a training.
But it won't be put into their original,
No, it's not in the original 3-phase certified water monitor quality training. Yes?
How do you get to, I mean, it was going fast and I didn't see,
Oh,
but
I'm
you
sorry.
get historical data, and is there any way you can manipulate that data as far as trends or seeing graphs or anything like that?
Yes, the best way to do that would be, if I can go back to our system. So if we're going to look at some historical data for nearby, you can choose to download data, which will download and open. It opens into a notepad but it's tab delineated, so you can then very easily open it into Excel, and from there manipulate that data any way that you would in Excel with any other program. Any other questions? Thank you very much. I think I've actually made up some time and ended a bit early. Yes. So I believe next is a networking break. Thank you very much for attending and viewing our new data viewer.
Okay, we'll take a little break and